So this is the final video lesson in this course where we pull everything together to create the software for our drawing machine. And this is done by creating a software module called Draw. So I'll just go briefly through the outline. We'll start with the requirements as we always do. We'll go through some design decisions and notes. We'll look at the API, which is in the header file. We'll look at the implementation, which is in the C file, and this is where we'll find kinematics and trajectory planning. Then I'll do a demo of the drawing machine working. We'll do motions in both joint and Cartesian space. And then finally, the prompts. So here are the requirements. I've got to say I kept them small. The basics are here, but not much more. The focus here is position control. There really isn't much speed control. It's just a fixed value. But these requirements are a good start to explore this area. So let's go through them. The first requirement is just the base one. We have to support a simple drawing machine using a planar two-link arm. Next, we have to support making motions from the current position to a final position with the following motion types: linear in joint space and linear in Cartesian space. This is the heart of what we've been working on in these video lessons. This is where we use kinematics and trajectory planning. As I mentioned, there's no requirement specifically for speed control. It can be very simple, and it is. We need to support a simple manual joint angle calibration procedure that works as follows. We need the ability to jog a joint by some specified number of degrees, plus or minus, to get the arm into a standard position. And then the ability to set the joint angles to 0 degrees for the current position. Note that joint 2 is the position where the two links are in line. As you'll see in the demo, we just use sort of an eyeball method of calibration. It's not terribly precise, but it's good enough. All positions in the API are specified in Cartesian coordinates using millimeters. Then there is the superloop requirements, because this module is in a superloop architecture. It uses the standard core APIs for module startup and the superloop itself. And of course, everything has to be non-blocking. That's critical for superloop. And then finally, we have support for test and debug, which is things like logging and console commands. Of course, console commands are critically important for this module because that's how we demo the machine. And then I have this requirement down here that the console interface should use millimeters for coordinates and degrees for angles. Internally, we use radians for angles because most math functions are based on radians, but people tend to think of degrees. So now let's get into the design, and we'll start with the API. So the most fundamental API is to move from the current position to some final position, which is specified with millimeter coordinates, and to do the move in either joint or Cartesian space. And then we have a couple APIs to support calibration. And I described that in the last slide. Basically, we have an API to let you jog a joint some number of degrees. And the idea is you will be jogging these joints to get all of the joints at the 0 degree position. And then there's an API to tell the module the joint angles are now at the 0 degree position, and that's calibration. So on trajectory planning, we have one move at a time is supported. We don't have a queue of moves like we do in the step module. The stepper motor speeds are constant, but they can be modified via the console. And what we're doing now is have a speed specified in milliseconds per motor step. And this is really crude, and we shouldn't be talking about motor steps at this level, but it works for now. And by the way, the default is 20 milliseconds for each motor step. For doing interpolation, when making moves in Cartesian space, there is a constant for how long each segment should be, and it can be modified via the console. The default is 2 millimeters per segment. The way the design works is that The module has a run function that is called from the super loop at a high rate typically. And what the module tries to do is keep the stepper motor command queues full. And the way it does that is if it's doing a Cartesian move, it'll just do interpolation until the queues are full. So it'll interpolate for, let's say, 2 segments. And if the command queues are full, then it stops. Since there is no active speed control, a move in joint space can be handled with a single set of stepper motor commands. So no interpolation is needed. It's very simple. And finally, here are the console commands, and I tend to have 2 commands: a status command to dump the status, and a test command to do, to test things out, like the API. And of course, we'll be using this test command to do the demo. Here is a cartoon-like view of the physical design. This is a bird's eye view, and notice I've drawn it on a Cartesian plane. And you might notice that in this figure, the positive x-axis points up and the positive y-axis points to the left. This is a little odd, but it's because when I was developing this, I was looking at the arm from a different perspective. But the video camera is set up like this, and it doesn't really matter. If you rotate this picture 90 degrees clockwise, then the axes look more normal. So you'll notice that the motor 1 is at the origin of the plane. The coordinates are 0, 0. You'll notice the lengths of the 2 links here in millimeters. And then you'll notice at the end of the arm is the tool point, which is a pen that draws. If you add these 2 lengths together, you get 268 millimeters. So that's basically the maximum reach of this robot, which is this dotted line. This robot could reach below this axis down here, although I don't have it really set up properly to do that, but it would be possible. So this slide tries to give a picture of how the system works, and this is applicable to the demo. So we have someone like me typing in commands at a console, and some of these commands are shown down here. I won't go through these, but these are some of the key commands in the demo. We'll first be calibrating the robot, which is these jogs and this calib, and then we'll be doing some moves, which are these 2. So the console commands go into the draw module, and if we look at the implementation, we'll see the implementation of these console commands, and then they will be calling the APIs, and these are the APIs they'll be calling. So when the draw module receives a move via this draw move to API, it will start sending commands to the 2 step modules it's connected to. And it uses this API to do that. And as you may remember, the step modules have a queue in them. So the draw module tries to keep that queue full of work. It sort of works ahead. And then the stepper modules execute the commands in those queues. And of course, they act on the motors to turn them. So now let's look at the API in the draw.h file. And this is pretty straightforward. We have an enum here, which defines types of moves, either joint or Cartesian. And then here is the data configuration structure for this module that is supplied during module startup. And the only 2 things in it now are an indication of which stepper motor instances are being used. And there's 2 of those. And then the lengths of the links. And there they are. And that's needed for the kinematics, of course. Now we get into the functions. These first ones are the core API. And this module has a run function that gets called from within the super loop. So this function here gets called at quite a high rate. And then here are the APIs that I discussed in the requirements and the design, and they're pretty straightforward. Here's, move to, jog joint, and to do the joint calibration. So now let's look at the implementation in the draw.c file. As I do in these code files, I just give a few highlights because there's too much to go through line by line. So we'll start with this enumeration here. This is the high-level state of the module, and there are three states. One is it's not calibrated. Until it's calibrated, you can't do a move because the arm doesn't know where it is. And then after it's calibrated, it's either idle or it's actively working on a move command. So next after that is this struct state, which is all of the data, all the variables for this module. And this is a mixture of some configuration data and some real-time state data, for example, as it's doing interpolation. The next thing I want to show you is the draw run. This is what's being called from the super loop at a very high rate continuously. And so what it does is first looks at the state. If the state is not calibrated or idle, there's nothing it can do, so it returns. If the step modules don't have any free slots, there's nothing it can do, so it returns. And then finally, it expects that the state will be active, and in that case it calls this function, which stands for trajectory planning continue, which typically would do some more interpolation and generate some more motion commands. So the next thing I would like to look at is this trajectory planning continue we just talked about. And basically this goes through and computes the next via point as it interpolates the move. And here we're talking about Cartesian moves. And then it does inverse kinematics. I can show you that here is the inverse kinematics to get it into angles. It converts the angles to steps and issues a command down to the step module. So one last thing I'd like to show here, which is very important, is the kinematics. Here's solve FK, this is for solve forward kinematics. These two statements implement those two equations when we were looking at kinematics. And then here is inverse kinematics. If you remember, it was quite a bit more complicated. And here is the math. You can go through this and compare it to the previous lesson on kinematics. So that's what I'd like to show you in the implementation. So here is the demo. You can see a live video of the drawing machine and you can see the console window. So the first thing I'm going to do is just press the reset button on the board. And there we see the reset messages. Now first we need to calibrate the arm. And we do this by getting both joints at 0 degrees and then calling the calibrate API. Note that we can't do moves until we calibrate. So I'm prepared for this and I know exactly how many degrees we need to jog the joints to get them lined up. And I'll just do that now. So I'm first going to jog motor 0, which is or motor 1, which is instant 0, 20 degrees. And you can see that move across. Now I need to move the other motor. Let me do jog 1. I need to move that 45 degrees the other direction. And you can see that moving. And at this point, they're pretty much lined up. That could actually, I might move that a couple degrees. There, that looks better. So now we just want to, we have it in the 0, 0 position, and we just want to calibrate it. And that returns success. And then finally, we can dump the status. And you'll see a lot of zeros here because everything is in the 0 position. And then this is the XY coordinates of the tool point. And that's a point 268 millimeters out on the x-axis. If you'll remember, the sum of the two links in the arm are 268 millimeters. So this is consistent with it being in the 0, 0 position. Now I've loaded some drawing paper and put down the pen. So we are going to draw straight along the x-axis. We are at coordinates 268, 0, and we're going to move to 50, 0 using Cartesian coordinates. And watch the joints operate as I do this, as they slow down and speed up. Towards the end of the move, joint 1 actually changes direction. So the command will be draw, test, move, 50, 0, and Cartesian. So not perfect, but somewhat linear. So now I'm going to move back to where we came from, 268, 0, but in joint space. Now notice in this case the joints move at a steady rate and do not change direction. So the command is draw, test, move 268, 0, and in joint space. Now I'm going to pause a moment while I move the arm out of the way. So there it is. It isn't great, but I hope you see the effects. By the way, when I built the arm, I made the links fairly long so I could make large moves. I thought that was good. The downside of that is the longer the links are, the more the backlash is magnified, and we're seeing the effects of that. But anyhow, in looking in Cartesian space, I think you'd agree the first line looks somewhat linear. The second one is linear in joint space, but not at all in Cartesian space. So I've put on some new paper, and now I'm going to try to draw a square. Let's see how well this works. With the pen up, I'm going to go to the starting point coordinate of 90, 60. So 90, 60. For this move, it doesn't matter what space we move in, but I'll just do Cartesian. So I need to move the pen down, and I'll just pause while I'm doing that. Okay, so when I put the pen down, I jostled the arm a little bit, which isn't going to help, but let's go. So the sides of the square will be 120 millimeters long. So we'll start by moving to 90 minus 60. So draw, test, move 90 minus 60, Cartesian. Okay, now we go to 210 minus 60. Then 210 plus 60. And finally back to the start at 90, 60. So again, I'm going to pause the video while I move the arm out of the way. So there you have it. It's not as bad as I thought. It looks pretty much like a squared. It's obviously skewed. And again, that's because of based on which direction the forces were pressing on those stepper motors, it would move one way or the other due to the backlash. So I'll take that. So now what I've done is I've moved the arm back to the original corner of that square, and I'm going to do the same moves, but this time in joint space, just to sort of highlight the difference. So again, we'll first move to 90 minus 60. And this time in joint space. And I'm going to prepare for the next move, which will be 210 minus 60. Joint. Then 210 plus 60. Joint. And then back again to the original 90-60 and in joint. I'll pause while I move the arm out of the way. So there it is. And it's pretty clear that moving in joint space doesn't give you straight lines in Cartesian space. And so I think that's what you would expect. And so that's the end of the demo. I think what this demo has showed us, if you're building a drawing arm with this design, these two joints, and you're using $2 motors, you shouldn't expect high precision. But it is a way to learn about robotics and kinematics. And so for that, it's just fine. Here are the prompts for this lesson. I'll just pause a second and then give you my take on them. How might we draw a circle? Well, the way I imagine it is we would have a new move API that would in some way give a center point and a radius in millimeters. And the software would then interpolate to create via points on the circumference of the circle. So in other words, it would segment the circumference into small pieces. Then we would perform moves to each via point in joint space, just like we do with lines. What is the mathematical relationship between degrees of backlash and error or uncertainty at the end of the arm? And this requires some simple trigonometry. So here is the model I have. I think this is correct. And over on the left, that would be the axis of the motor or the joint. Theta is how much backlash there is, and so that means this arm can go sort of back and forth this much. And these two lines represent the range of the position of the arm. And then out at the end of the arm, this is the amount of uncertainty. And I think the calculation for E is this. And I believe these variables are pretty self-explanatory. And as an example, if theta is 1 degree, and R is 250 millimeters, which I think that's approximately what it is on the demo, then this E could be 4.3 millimeters. So it just means that we don't really, there's this much uncertainty in where the tool point, for example, actually is. Now, in reality, we could know what it is because depending on which way the motor approached the endpoint, we could certainly reduce the amount of uncertainty. But that's a complicated problem, and so in general, this is what it is. And I mentioned here, error can be worse with several joints on a single arm. In our case, we actually have another joint about halfway through, and I believe that will then enlarge this uncertainty range. What are some physical constraints that are not handled properly in the software? How could they be handled? Well, there might be several, but the one that's obvious to me is if you rotate joint 2 too much, the pen holder will hit the first arm link. And in terms of how would we handle this, well, this is sort of an easy case because we can see it easily, and all we would have to do is put rotation limits on joint 2 in software. So that, for example, when we were doing a move, if the angle of joint 2 exceeded that limit, it would refuse to do the move. Now, we could also install, especially if it was a bigger robot, we could install physical limit switches that would cut power to the motors if a rotation limit was exceeded. So that would be a little bit of a backup on the software. Well, this is the end of the video lesson and the course on stepper motors and robot kinematics and trajectory planning. I hope you enjoyed it, and thanks for watching.